Namaste, I am JV'n Swarnima. Today we will discuss about introduction of strain energy method. Now, what is strain energy? Strain energy basically means energy stored in an elastic body under loading. Now, what is strain? Strain is a Greek letter. It is used to measure deformation of any body that is subjected to a force. It is generally defined as change in length divided by initial length. Strain is denoted by capital E. Capital E equals to del L upon L, where del L is change in length and L is initial length. As we can see by equation 1, strain is a dimensionless. And as per Hooke law, strain is proportional to stress producing it. Now, change in shape of any elastic body caused by application of external force, that is axial load or moment, then if the external force is greater than the elastic limit, yielding take place. But if the external load is not greater than elastic limit, the work done in straining material is stored in it in the form of internal strain energy. Now, where the internal strain energy is stored? The internal strain energy stored within the recoverable part of stress strain curve. Now, what is stress strain curve? Where it comes? Stress strain curves from stress strain diagram. As we can see here, there is a stress strain diagram. Stress strain diagram is a graphical representation of mechanical properties of material. In this diagram, we can see point A, which denotes proportional limit. Point B denotes elastic limit. Point C denotes yield point. Point C dash denotes lower yield point. Point E denotes ultimate strength and point F denotes rupture strength. Now, what is OA reason denote is OA reason denotes linear deformation. OB reason denotes elastic deformation. BD reason denotes perfect plastic reason. DE reason denotes strain hardening. Reason denotes necking. Now, what is stress strain diagram? How it is plotted, and what is the meaning of this diagram? The diagram begins with a straight line O to A, in which the stress strain relationship is linear. That is, strain and stress are directly proportional. Point A marked as limit of proportionality, beyond which curve becomes slightly curved until point B, the elastic limit of the material is reached. Region AB is non-linear region in which stress is not proportional to strain and the elongation increases more rapidly. However, up to the point B, the removal of load would result in complete recovery by specimen of its original dimension. If the load is increased further, yielding takes place and the point C is the point of sudden large extension known as yield point. After the yield point stress is reached, the ductile extension takes place and the stress increasing at an accelerating rate as represented by C to D. Now, in this region, C to D region, there is no noticeable increase in tensile force. The material becomes perfectly plastic in this region, which means that it can be deformed without an increase in applied load. If the load is further increased, the steel begins to strain harden. During strain hardening region, the material appears to regain some of its strength and offers more resistance, thus requiring increased tensile load for further deformation. After D, with further increase in load and extensions, the point E of maximum load or ultimate stress is reached. Up to the maximum load, the bar extends uniformly over its parallel length. But if straining is continued, a local reduction in cross-sectional area occurs. And as the load is concentrated at this reduced area, a considerable local extension also take place till the failure or rupture take place at F. The breaking load divided by reduced area of section is greater than the maximum load. This is about the stress strain diagram. Now, the area above the stress strain curve is known as complementary strain energy, which is this part. For a linearly elastic material, the complementary strain energy and elastic strain energy are same. That is U star, which is complementary strain energy, is equal to U elastic strain energy. For determining deflection, energy principle can be used by equating external energy to internal strain energy. Now, the first is strain energy due to applied load is U equals to 1 by 2 P del, which is strain energy is equals to work done, and work done is force into displacement or deformation. So here U equals to 1 by 2 P, deformation is del. Del is equals to PL upon AE from Hooke's law. U equals to 1 by 2 P into PL upon AE. Now U equals to P square L upon 2AE, where we can consider a bar where in which the length of bar is L, area is A, axial load is P, del is deformation, U is strain energy. Total strain energy when area of bar is variable, then U is equals to integration of integration limit of 0 to L P square dx upon AXE into 2. Now, the second is strain energy due to moment or couple. When moment is applied on an element, there is a change in slope. So, du is equals to 1 by 2 m into di, which is di, where di is change in slope. Now, the final formula is u equals to integration limit 0 to L m square dx upon 2ei. Thank you.